what are the what you can say takeaways of this FDP? Do you need any changes in this thing or what? Yes. Anybody? See, if it is not interactive, it is not a good idea to proceed then, right? Because we always keep on speaking in the classrooms, right? All of us, all of us. But here, particularly, we are here to discuss certain basic stuff. So, yeah, social. How are you?
Sir, are you asking to me?
Yeah, I just saw you, so I asked you.
Okay.
Hmm. Is there a problem in network or what? I think his network has got some problem, right?
Hello, am I audible, sir?
Yeah, Manish, please.
Yes.
You are asking
So,
something?
sir, yes. So, sir, so you asked, okay, what is the experience so far?
Right, right.
So, yeah. First of all, I would like to say about myself. I am not able to, so in advance, this program is like in advance. We have to read the chapters. We are supposed to read the chapters fully and
Right,
then
right.
attend session. So
Correct.
that is my limitations for last couple of sessions. I missed it that part.
Mhm.
But what I feel so far is actually we need more interaction kind of session rather than mentor is just explaining things that is written or that
No,
is
no, no, no.
given in the
Yeah,
chapters.
of course. See, the basic idea is that it is not regarding presenting anything or discussing any particular
Yes.
topic, right? It is
Yeah.
about
Yeah.
basically it is about if you have got certain confusions or questions regarding certain topics, right?
Yes.
Then those can be discussed. Sometimes if you have certain linkages, particularly there are chapters where you have got applications in other fields as well.
Yes.
So
Yes.
explore those linkages and try to validate those linkages with
Input.
your mentor, right?
Yes.
Sometimes it happens that we think of certain particular link, right? But we are not sure whether it will work or not. So those are the things that we can discuss here. That is the basic idea. It is not
So,
about presenting what is written in the book. It is already there with everyone.
yes. So, I mean, for me, I would suggest that each mentor stimulates the discussion in a way that these topics that whatever we are discussing can be implemented in whatever field, then it
Right.
might be more interesting that way.
Okay.
And
So
the other thing I also,
some application side.
yes, yes.
Okay.
And the other thing I also discussed with Manan a bit. So, so in one section, if we can, if we try to cover two or three like three chapters, it
Mhm.
is.
It is
I don't
difficult.
think we can
Yeah,
able to.
I can understand.
I mean, for me, it is.
No, for anybody it would be like that. Of course.
Yes.
That is there. That I think that we already had in mind when we saw the timetable, right? But in itself, any FDP going for 6 months itself is a very large period. So we have to somehow manage the things. But see, the basic idea is not to cover everything which is given in those chapters. Take up one particular topic and then try to discuss that thing. That is the basic idea. Obviously, we cannot do each and everything which is given in all those chapters. It is almost impossible.
So yes, sir, I wanted to say that.
Yeah, I cannot hear anyone. I think.
Actually, I'm also traveling, so there might be a problem with the.
Yeah. Fine. No, not an issue. If anybody else has got anything to tell, then we can have a few, 1 or 2 minutes for that thing, and then we can start.
Hello, sir. Am I audible?
I'm fine, sir.
Yeah. But I cannot see
Yeah.
you.
Yes. Um, yeah. Here actually, the room is dark, so it is not.
No, not
This
an
is
issue. Not an issue. Yeah.
okay. So just I want to say that if in any chapter, okay,
Yeah.
some part actually is given to all the participants, like it should be distributed to all the participants, and
Hmm.
some time is given, like 10 minutes or 15 minutes, so that he discuss the thing. So in
Okay.
this way, all the person will be in the session in the active mode. Right?
Okay.
So this is my suggestion that some part actually should be given
So you mean
of
to
all.
say some kind of assignment live in the
No.
session
No.
itself?
So, for example, suppose chapter 4. Okay, so in chapter 4, some part actually
Okay. Some part to be given to some particular participant, right? And
participant, and then he will discuss about 10 minutes. So 10 minutes, so 6 participant we can
okay.
consider. So
But
another
I
one
think,
1 hour, yeah, another
yeah.
1 hour, then the mentor will discuss the same.
Okay. Yeah, that's a good idea. But how practical is it? That is the question again. Because if we restrict that, okay, every particular person will be discussing about 2 3 topics, then in principle you will be talking about all the topics which are given in those chapters, so it won't be possible for anybody to cope up with all the people. And there will be another issue also, that some people will feel that, okay, I also had prepared, but I was not getting any, I was not given any chance to interact with the other people, right? So
Right.
practically what happens is, we may not choose all the topics from the chapter. You can choose particular topics only, even right now, not an issue, right? But what is most important is that how much is your understanding regarding that particular topic, and where do you apply those things in your current teaching or anywhere as such, right? So that can be taken up, but it will happen if and only if it's a physical classroom kind of interaction, then probably it will be a better option, what you are saying. Because then everybody will be participating in everything. So even if somebody is left out, it will be okay, fine,
Yeah. That's it.
right? But I think that can be taken up that way, not an issue. I think Manan is listening, so he can decide about that, right? You can choose 1 or 2 topics only, and then you can start. In fact, that was the original plan. It is not necessary that every participant will be actually contributing in every chapter. It is not so. You will have your own choice of field, your own choice of topic. You can read about those things, and then you can discuss. But in doing so, what might happen is, many topics will be completely left out, and many topics there will be so many takers, right? So the idea which you are giving is perfectly all right, in that sense that, okay, we can cover all full spectrum of all the topics, right? But again it will be dependent only on the participants, how far they can take it to, right?
Yeah.
Because
Yes, sir.
yeah, and particularly today's topic, if you see carefully, the topic's name itself is basic physics. So in my opinion, you don't need to do any preparation for this thing, right? Is it needed?
Yeah. Not required.
Is it needed? Yeah. But what I have done is, I have tried to create few slides which will just trigger the discussion. It is just to trigger the discussion. It is not about presenting those things. It is not even in formal presentation type of thing also. What I am doing is, I am trying to put those things in some introductory thing, right? Just points, not even the full content is displayed or anything is given here as such, right? But have you gone through the second chapter of Feynman lecture series? Second chapter, basic physics. Let me present the thing which I shall we start, Manan, now?
Yes, sir.
Or
Around 20,
because,
20,
yeah,
20,
I can see
20
20
participants.
participants, 20, 22 participants. So if you want, we can wait
No,
still.
no, sir. No, no, sir. No, we can start, sir.
We can
We
start,
can
right?
start. Yes.
Okay. So what I'm trying to do is I'll just try to
Share.
present. Yeah. Can you see the slides?
Yes, sir. Yes, sir.
Yeah. Shall I turn off my video so that
Yeah. No
our,
problem, sir.
yeah, what you can say, our bandwidth is not becoming an issue then, right? Am I
Yes.
audible?
Yes, sir.
And the screen is visible?
Yes, yes.
Yes, sir.
Okay, fine. See, the basic idea is that we would like to have uh, discussion regarding basic physics. And if you have read the chapter, the basic idea is that how the physics got developed up to this stage throughout the lifespan of humanity, you can say, right? So that is what is basically given in that chapter, and it is given in a very nice way. Feynman has got his own way of explaining the things. But what we are trying to do is we'll try to link those things with certain things which are not even given there. So I have started with somewhere, even he did not talk of in that era, right? And the rest of the things will be taking up, and I have gone beyond whatever he has discussed, because if you see carefully, these are the lectures which are basically in 1960s, 60s, right? 60, 62 or something like that. That was the time period in which we were talking about when it comes to Feynman lecture series. And because we are talking about basic physics, we have gone much beyond that point, even after 1960s. Okay, particularly our focus will be more on modern physics, you can say, right? Or means automatically quantum mechanics and particle physics and other things will automatically come in the way when we talk about such things. So just to start with the basic thing, uh, just a minute, a minute, yeah. Okay. Actually, I am getting now it's fine. Yeah. Is it visible now?
Yes, yes, sir.
Okay. Now see, if we just break up these words, science. So science basically means knowledge. When you talk about physics, physics basically means nature. Both of these are basically coming from Latin and Greek word.
Yes.
So the moment we talk about physical science, you are talking about knowing about nature, right? Now, this is basically all about what, how, and why. Okay. You are just trying to observe what is happening around you. Then you are trying to carefully observe and just identifying how it is happening, right? That means in what way it is happening. And lastly, why it is happening. Is there any underlying rule or law of nature which is allowing it to happen or which is forcing it to happen, right? That is all science all about since beginning. Okay. So when you talk about our evolution, right? You observed many things which are happening around you, then you try to find correlation between some similar phenomenon, right? Define laws and try to understand and predict certain things, right? Whatever you identified as a mathematical identity, try to reproduce that thing uh, using those laws. Okay. Then analyze the result and modify the laws to explain it in a better way. Use established law to find or to study matter and basic interaction. Apply knowledge for betterment of life, right? Acquire more and more knowledge and build further. And then you have got these all things which are basically coming from basic pure sciences. Okay. So this is something that we already know. I have just listed it here. Okay. But now if you talk about Feynman's way of explaining this thing, what he says is that you visualize this thing, right? that, for example, if you talk about a scientific investigation, what are the things? So first thing is you are observing something in experiment, right? And then whatever you observed from the experiment, you are trying to put some deduction, you are trying to make laws, and then again you are trying to do the same thing. So ultimately, whenever you talk about any scientific investigation, the ultimate thing is the experimental observation and whatever you deduce from there. Okay. So this is the basic idea, which is basically shown by Feynman. What he says is that if you are trying to understand what is happening in nature, as we discussed in the first slide itself regarding the physical science is you are trying to know about the nature or how nature is behaving and something like that. Okay, physics itself means nature. Now, this is Feynman's idea as he presents in that particular chapter, right? Chapter 2, Basic Sciences. That, for example, suppose if you are given this thing that, okay, two people are playing chess, okay, and your job is just to identify what is going on, okay. So very first thing is that, okay, for some time you will observe that thing and you will identify that, okay, this is the kind of game where two participants are basically moving this pieces one by one, right? That is the first thing that you will observe. So that is first observation. Then after a longer observation, you will identify that, okay, there are certain rules which are followed by this particular game. Okay, that a pawn will be moving like this only, right? A king will be moving like this, a queen will be moving like this, a bishop will be moving like this, and so on. So you are trying to identify this thing. Now, ultimately, what you will do is you will, after a long observation, you will identify that, okay, these are the rules by which this particular game is played, right? So we will call that these rules are basically the basic laws of nature that we understand. And we are trying to put them in mathematical form and so on. But the basic idea is that will you, after knowing everything, will you be able to actually identify that what will be the next move of the person? Probably no, because he is using the laws. He is not doing anything which is beyond the rules of the game. He is doing according to the rules of the game. But you really don't know what he will do in the next move, right? Because that has got so many complicated relationship between all those rules and the way he wants to take the game further. Many things are there. Okay. Similarly, we normally talk about the basic laws of nature and we see them piecewise, we see them separately. Sometimes we combine them as well, right? But at the same time, when we say that we are talking about uh, any natural phenomenon happening, that natural phenomenon is not using only one of the rules. It can be using multiple types of rules, and probably it might be using a rule which is a special rule in that particular condition, right? For example, if you have played chess, a pawn will be normally moving by one step only, but that will be moving forward. But if it wants to kill any other piece, then definitely it can go in a crossed way as well, right? Sometimes you will see that, okay, queen is able to move everywhere, but the king cannot move. But when it comes to getting a check kind of thing, then king also can move. King cannot move to kill somebody or kill some other piece or something like that. So there are some special cases. So normally whenever we come with physics part, we will say that, okay, there are some selection rules and there are some, say for example, there is uncertainty principle, there can be Pauli's exclusion principle. These are all special cases in which the particles behave in certain way. Okay, so this is how Feynman tries to explain this thing, that just by looking at what is happening, it is directly not possible to fully understand what is happening all together in all cases, right? And more you observe, more and more you can correlate with whatever is going to probably happen next. Now, if we just quickly go through the milestones, now these are the milestones where which I am trying to put all the things together, and in which whatever Feynman has covered, I have basically tried to keep them in faster pace. But rest of the things where from where he starts, right? I have taken the points in little deeper detail when it comes to a part from where or part before the Feynman starts that thing. Okay. For example, if we talk about the milestones, see, basically physics means, when I say physics, okay, so you are basically talking about matter and forces, right? So initially, when we talked about when people thought about science and other things, right? So these were the initial points. So this is basically 600 years before Christ. Okay. So the idea was that everything has a cause and water makes everything. So initially people were basically thinking about religious things, right? So whatever is written in the whatever is written in religious scriptures, they will just believe those things. Whatever is the mythological thing, they will believe those things. But this was the first person to identify that, okay, there has to be some underlying rule. Everything has a cause, everything has a reason to happen, and it is water which makes up everything. That was the first idea. Later on, these were his students only. They identified that it is not only water, it was basically earth, water, fire, and air. Four elements basically were there, and they were governed by forces. So they required forces as well as matter, right? So that happened just in 600 BC only. Okay. And forces were basically called love and strife. Now, in India, at that time only, the idea was that these four were fine, but there was Akash or space, as we know today, right? So that's why we say that there are five elements to the existence or something like that. Then, in then there was another idea that there was something called epiron as a basic element of matter, right? So this was also another idea. See, water was considered to be continuous kind of thing. Okay. So ultimately it was identified that, okay, your matter which you talk about is typically grained. Okay. Or this is basically indivisible, eternal, unchanging, and not caused by anything. It is always there. It has been always there. Something like that. Okay. Then in 500 BC, it was basically the first time when there was an address to something called time, right? Even today, if you really see the definition of time in, say, Wikipedia, it is basically talking about sequences of events and something like that, right? It is a kind of little complicated definition of time. Feynman used to tell that time is basically something which continues to happen even if nothing else is happening. Okay. And that is a genuine definition, we can say. But it was 500 BC when this particular idea was coined for the first time, that you require some sequence of event which is irreversible, right? And then the basic law which was given by this Heraclitus is principle of change. Aristotle, everybody knows, he was the person who was behind the observation of physical phenomena, and he told that it can reveal the natural laws governing them. If you observe the physical phenomena properly, that means basically experiment, right? He gave geocentric view of the universe. That means the earth was the center of the universe. Then his student, okay, I think his student or his follower, he gave heliocentric model of universe, this, right? Aristotle. He told that sun is basically at the center of our solar system and earth is moving around it, and there are other planets as well. But planets definitely were not coming in those things at that time. Archimedes was one of the greatest, what you can say, contributor to science in those days, right? This is again, we are talking about 250 years before Christ. So hydrostatics, statics, lever, he worked in all these things, and he was the first person to tell that mathematics and nature are inseparable, and maths is definitely inevitable part of physics. Sometimes, see, before that time, before Archimedes, everything was looking like it was a kind of philosophy only, right? But he was the first person to tell that, okay, you cannot talk about science without, or nature without mathematics. So idea was to identify certain rules which can be followed, which are followed by the nature, or which are there in the nature. He calculated the area under a parabola. We call it integration now, right? He precisely could calculate the value of pi by mathematical things that he developed, right? and he basically developed the principle of equilibrium states and centers of gravity. He gave all these ideas, Archimedes, right? And basically, it was the foundation for Galileo and Newton. But remember, Galileo and Newton came in the 17th century. So, really far back in time, these ideas were already floated by Archimedes. Then, 200 BCE in India, Kanad was there, right? He also gave kind of systematic theory of atomism, okay, including some detailed maths and all. And he talked about this particular thing, Anu and Parmanu stuff. Then Hipparchus basically gave geometrical techniques to map motion of stars and planets. So basically, this was the astronomy thing. So in 150 years before Christ, they started calculating all these things, astronomy as we call today, right? And he could even predict the solar eclipses properly. Then Ptolemy, he wrote some detailed write-ups after the developments in astronomy. Aryabhatta, we know it, he introduced zero in the number system, and he also talked about the Earth's rotation on its own axis. Okay, so that was basically again in 500 CE. Now we are after Christ. Okay, then in 1000 CE, when you talk about this thing, so after 500 years or so, right, whatever was discovered, they were basically used. But many times it happens that in civilizations, all the scriptures or all the things that you have written, they got destroyed, and many things happen. Okay, so that happened with all of them. That happened even with Socrates as well, right? For example, as far as Socrates is concerned, whatever he talked about, more than 150 items were there, and out of them only 30 were available at the end. So it happens with all the scripts or whatever documentation has been done. So in 1000 CE, modern optics and visual perception were basically starting. Okay, and then a theory of projectile motion was also given. These were two by people who were in Arab Emirates, what UAE, what we call today. Okay, then when you talk about the scientific revolution, then it started in basically 1500s, right? So the science as we use today, the science as we know today, it started in 16th century, you can say. So Copernicus talked about the revolution of celestial spheres. So here comes your actual, what you can say, astronomy plus stellar objects. Then Kepler, we know that he talked about the laws of planetary motion. And in 1600, again, Galileo Galilei performed experiments and gave mathematical formulation to motion. He also studied about the properties of space and time. Okay, he did observational astronomy as well. We know that he developed telescopes and other things, right? Then in 1650, Descartes basically talked about the particle nature of matter again, right? So very long back, people told that, okay, the matter is grained. Descartes told that, okay, everything is grained, including energy and whatever you call it, right? Huygens, as we know, he gave the wave theory of light. Isaac Newton, obviously, laws of motion, calculus, optics, he did contribution to a lot many things, right? In 18th century, you had Joseph Black and Cavendish, who basically developed thermodynamics. So thermodynamics, as we know today, was developed in 18th century. Now, if you talk about say 1800, the electric battery was invented by Volta. Then John Dalton in 1819 basically proposed that, okay, everything is made up of atoms. Atoms means indivisible in Greek. Then 1820, Oersted basically identified that, okay, magnetic field is somehow related to electricity, right? It was an accidental observation that whenever lightning was happening, the magnetic needle was rotating fast. So he identified that, okay, if magnetic needle is rotating, that definitely means that somehow electricity, that lightning is related to magnetic field. Then in 1821, Faraday came in and he talked about electromagnetism. He tried to kind of what you can say unify the electricity and magnetism. Then in 1840, you have Mayers and Joules. They developed thermodynamics further. Maxwell, everybody knows, he basically contributed a lot in terms of electrodynamics or classical electrodynamics as we study in our master courses today. Then in 1859, Mendeleev proposed the periodic table of elements. And up to that point, fine. Now comes the birth of modern physics. Modern physics means the physics as we know today, basically from 19th century onward. X-rays were accidentally found by Röntgen in 95, 97. Thomson discovered electron. He basically gave the so-called plum pudding model where he told that, okay, all the atoms which basically this John Dalton talked about, the atoms are not only final things, they are also made up of something else. And so he gave the so-called plum pudding model that basically, that is something that we already know. Okay. Then Max Planck, he talked about the quantization of electromagnetic energy, right? He gave us the famous E equal to h nu. Okay. And remember, when he tried to solve this thing, his basic idea was to solve the experimental observation which was observed in black body radiation, right? Their intensities of various wavelengths were not matching with whatever was basically shown by Rayleigh's law. Okay, so his idea was to somehow mathematically at least give a kind of theoretical formulation where you can explain what is happening in black body radiation. So he told that, okay, if you are saying that you have got waves and particles, right? Because that came along with our evolution. We ultimately thought that everything has to be made up of either continuous thing or discrete thing. Then discrete and continuous were finally coined or converted into, you can say, wave-like and particle-like. Discrete means particle-like and wave means continuous one. Okay. So whenever you talk about energy, it was considered to be continuous. Whenever you talk about matter, it was considered to be discrete. So that wave and particle thing basically came in the thought process. He was the first person to tell that, okay, a radiation also can be quantized, and he gave this E equal to h nu that everybody knows. Then it was Albert Einstein in 1905 who talked about the photoelectric effect, special relativity of theory, and special relativity. Then he talked about the Brownian motion. He gave mathematical explanation to Brownian motion. So these were, no doubt, these two were not directly related. Means this particular Brownian motion is not directly related to the modern physics, but because it is Einstein, I just wrote those things here in the flow. Okay. Then when you talk about evolution, it was in 1911 where Rutherford was basically trying to do that famous alpha particle scattering problem, and he gave the planetary model. In 13, Niels Bohr basically gave atomic model. 16, Albert Einstein gave general relativity. Louis de Broglie talked about matter waves. Again, you must be knowing this thing that Louis de Broglie was basically a student of history, right? And because his elder brother was working in physics, he also got interested in physics, and he told that I want to do my master's in physics again. Then he did his PhD, and his thesis was initially outrightly rejected when he told that electrons also can behave like waves, right? So basic idea is that his matter waves were not initially accepted as such, right? But later on, basically, it was Einstein at help. He told that, okay, you try to just check whatever he says. If he says that your lambda is equal to h by p, right? You can try to accelerate the electrons in such a way that it will have a particular defined lambda, and try to see whether it can give you some electron diffraction pattern or not, just like X-ray diffraction. And it was experimentally identified that yes, it does give a diffraction pattern. So it was practically proven, experimentally proven, that electrons were behaving like waves. Okay. Then in 1924 only, Erwin Schrödinger basically talked about, or he basically came at or arrived at the quantum mechanical wave equation as we know today, right? Then it was Paul Dirac in after 4 years, because Schrödinger equation was not basically consistent with special relativity. Okay, so Paul Dirac basically again identified certain lacunas, and he he came into development of this relativistic quantum mechanics. And in doing so, he had identified in the theory itself that, okay, there must be something called antimatter available. And experimentally, it was discovered 4 years after that. Okay, the positrons were identified in cosmic rays. Then the mass of the nucleus was not coming as per the understanding, right? And it was difficult to identify how the nucleus is so tiny and it is keeping so much of mass inside. Neutron was proposed, and then after that proposal, Chadwick identified this thing experimentally in 32 again. Yukawa proposed pions physically, and pions were considered as the exchange particles between protons and neutrons and protons, which were basically responsible for nuclear force. Okay, then in 47, Rochester and Butler basically discovered something called K mesons or kaons, right? They are special because they contain something known as strange quark, right? And strange quark is really strange in certain way. We'll discuss that thing as and when your questions come up, right? And then at the last 1964, Gell-Mann and Niemann basically presented the so-called standard model of particle physics. So this was a very quick review of whatever happened since beginning to the standard model. No doubt, beyond 64 also there are a lot many things to discuss, but that we will be discussing directly. Okay. So the question is, when you talk about this thing, or when you talk about this wave particle duality, let us say, what is your take? What do you understand by this wave particle duality? And do you think that there is any kind of confusion regarding this particular terminology, wave particle duality? Anybody? Now it is my term of talking is over. I just went quickly through the developments, the milestones of development of physics as it is today. No doubt, it is not as it is today. Certain things are yet to come. But in between, just one slide I wanted to discuss. Yeah. What is wave particle duality and why it was required? Anyone? What is wave particle duality?
Hello, am I audible?
Yes, yes,
Yeah,
yes.
actually, in some cases, um, we just actually we consider like a wave, right?
Okay.
For example, if we have the uh, electromagnetic wave, okay.
Mm.
So in explaining this electromagnetic wave or light,
Mm.
we use the wave behavior. So
Okay.
when it is moving in the space, okay,
Mm.
so we say that it is a wave. But as soon as it interact with the another particle,
Right.
then it will change like a particle. So we need these two things, I believe. So it is like a state. So one state is like wave, another state is like particle.
Okay. So
So
I
this
basically,
is
think,
why duality? See, as you are
hello.
saying,
yeah,
at a
yeah.
given
So
time,
actually,
it is
somehow,
either wave or particle, right?
yeah, yeah.
Okay.
Actually,
I
somehow the same thing is containing two behavior. One is appearing at one time and another is appearing at another time.
But
So it has
none of them is happening at the same time, right? In no case. Either they are behaving like
simul-
particle or they are behaving like wave. Simultaneously, they are not seen together.
to explain the experimental result of such a phenomenon, experimental data that we have obtained in the end of the 20th century, I think matter and radiation can behave as a wave and particle both, but
Mhm.
to it is depending upon the various experiment. Like if we want to explain the young double slit experiment with respect to electron, then definitely we have to consider the wave nature of electron. But in the same way, if we want to explain the photoelectric effect result, then we must have to consider photon as a particle. So it is completely depending upon the situation at what
Okay.
experiment we are dealing with. So that is what a
Okay.
wave particle duality means, I think so.
Okay. Yeah. Now that is good enough. That is good enough. My question here is from in a different scale altogether. Let us just try to understand one thing. That do you believe that it was humans only who decided that okay, whatever we see around us has to be either particle or wave, right? Right?
Yes, sir. Yes, sir.
Yeah. We
Yes,
only
yes.
means in the course of development or understanding of science, we identify that it has to be either wave or particle. It cannot be anything else. Okay. Now let us try to see this particular example as we discussed. Right. Assume this thing. Now, this is a very intriguing example. No doubt, it is not my own example. It is the slide I have prepared, but the idea is basically coming from a book. I'll be just revealing that book after this thing is done. Assume assume that there is one alien world somewhere. Okay, it is some alien world somewhere, and they are definitely much more advanced technologically than what we are. Okay, and this is our Earth. Fine. Now, the basic idea is that the people on this alien planet somehow come to know that there is a place called Earth, and there are people on Earth. They are basically what you can say. They are uh, uh, interacting with each other. They communicate with each other using some words. They speak. That is how they identified from there somehow, right? So what they wanted to identify how do these people on earth communicate with each other. Okay, they wanted to identify this thing. Anybody has heard of this particular example earlier?
No, sir.
No. Okay, then probably you will enjoy it better. So the basic idea is that this is an alien world, right? We really don't know how do they communicate and how do they work, but they want to somehow identify that what is the way in which the people on earth communicate with each other. Okay, so they basically sent a probe to earth. Okay, and the probe basically went into say France. Okay, and then it remained there for say 1 year or so, and obviously we could not identify that that kind of probe is moving around, right? And it told that okay, I am this particular word is spoken, so it is collecting and recording the words. At the end of the year, it basically collects all data and goes into their own planet, and those scientists identify that okay, people on earth basically speak these languages, and they call it French language, right? So their experimental data was telling that people on earth speak French. Okay. Now, science is not a thing where whatever I say, you will simply agree. You have to tell that, okay, no, I also want to do it experimentally. I also want to test it. So there was another group of people on the same planet. They also told that, okay, we also want to send one more probe, and we want to experimentally verify what you are saying. Okay. So they sent another probe. That another probe also came to the Earth, but this time it went into Germany. Okay, so that probe is in Germany now. That probe roamed around in the whole Germany, and it collected the words, right? And experimentally, after a year, they identified that people on earth speak German. Now, see, people on earth speak French was an experimental evidence. They had correct recorded voices. People on earth speak German. They also had again the same experimental proof. So none of them can be denied. Obviously, whenever such thing happens, what will be done? A third group will tell that okay, we would like to check who is right. Okay. So by chance it happens that that third group also is sending a probe to Earth. Okay. And that probe comes to America. Now the thing is that America is a place where most people basically came from either Europe or UK as we call today. So their native languages were either French and German. So whatever interaction they had, ultimately your English language came into existence using only the words which were available in French and German. Now that third probe is having now two lists available. One is German words, the other is French words. And now it is trying to identify which language this person is speaking. So he can see that, okay, people on earth speak German and French simultaneously. In the same sentence, you are having words that are basically belonging to French. You in the same language, in the same sentence, you are having the words which are German. Okay, so they called it French-German duality. Right? Now I hope you are getting what I'm trying to say. See, people on earth don't speak only two languages. There is a good chance that that probe might have caught into Gujarat. Even in Gujarat also, you have got various slangs in which Gujarati is spoken. If it falls into Tamil Nadu, if it falls into Delhi, if it falls into Assam, everywhere there is a different language, right? So now if you think carefully, see, whatever we talk about atoms, okay, it is nobody has actually seen that there is one proton and there is an electron which is moving around it. Does anybody have any kind of picture like that? No. We assume that it is that way. And if it is happening that way, then these are the consequences of that thing, and experimentally we can identify those things. So we are basically trying to see everything in a completely different way. Okay. So the basic idea is that in particle physics or in our general quantum mechanics in general, right, we cannot say that there is only wave and particle. Your particles can be Gujarati also. Why not? It is our own limitation that we told that, okay, it has to be either particle or wave. It can be something else. Third thing, we don't know, right? So wave particle duality, when you talk about, it basically creates so many confusions as such. But at the same time, it solves multiple problems. So in a given problem, your particle is either particle or wave. It is not both of them at the same time. Then technically speaking, why can you use the word duality there? It is something else, right? It might be something else. Okay. This particular example, this pictorial representation is mine, but this particular example is basically from this particular book, Science Matters by Robert Hazen and James Trafford. This example is given there. And I very much like this thing because, see, we do not know what is happening. You might have seen that orders or powers of 10 video. Have you seen it on YouTube or anywhere? There is one video of powers of 10. Have you seen it?
Yes, sir.
If you have seen it, you could recall that if you are on the ground, if you go up by powers of 10, that means first you are here, then you are at 10 meter, then you are at 100 meter, then you are at 1 kilometer, and so on. And if you go up to the end of galaxy and beyond that, right, then whatever you see there will be exactly looking same if you go into the atom, right? Finally. So basic idea is that we are not aware of what exactly is happening at infinity distance in this space. And really, again, we don't know what is actually happening at the very core of matter. We don't know how exactly a nucleus look like, right? Suppose when we say that, okay, how can you think about, or what can you think about a proton, for example? Everybody knows that proton is made up of up, and down. 3 quarks are there. Okay. Now, if proton is made up of 3 quarks, then how is it possible that a proton is a spherical thing? It must be some kind of triangular thing only, right? Doesn't matter how you arrange 2 or 3 points, it will make a triangle only. But whenever we think of proton or neutron, we think that it's a spherical thing. Okay. So if you try to put everything very properly, then again your wave particle duality comes in a problem. It cannot explain certain things. Okay. So according to this explanation, wave particle duality word is our own way of uh, looking at the things, and it is a limited thing. For example, this is French-German duality. Actually, it was English. It's a third language, right? Doesn't matter. It is matching with, many of the words are matching with them. Okay, is it clear? Basic idea is that wave particle duality is our own limitation of explaining the things.
Sir, I have a question.
Yeah.
Minor query. Sir, when you are talking about, see, protons are made up of two quarks and one down quark. Now, means as you said that it should be something triangular or something or any other shape, but
Yeah.
not spherical.
No, that is
I just want
no. Again. Let me first complete that thing. If you assume
Okay,
that they are particles, grained thing, then that has to happen. Right? This is just this is just a milestone. Even right now, today, if somebody is working in particle physics and if you ask that what are particles, then they will say that they are excitations in the field. Particle physics में particles है ही नहीं.
ground
Right?
state excitation.
No. We will talk about that thing just after one or two slides. Okay.
Okay. So I was coming to that. Basically, the field concept I was coming to. Okay.
Correct. It is basic. See, right now the basic thing which is pursued is quantum field theory. It is so it gives you all the freedom from all these confusions. Wave particle duality is a confusing concept in itself, right? But at that time it was working. And normally duality, whenever we use word dual means it is happening at the same time. We know that wave particle duality, it is not happening at the same time. For example, if you talk about a photon, when it is generated, it's a photon. When it is traveling, it's a wave. And when it is absorbed, it is again a photon, right? So at the same time, it is not both of them, right? Okay.
Yeah, it's
So
just a
let us
manifestation of the same thing in two different ways. Like we talk about
correct.
the dual vectors or
Exactly.
something. So
Exactly.
in different spaces, they have the different identities.
Exactly. But that is the thing. Then that cannot be called a duality. That has to be called something else. It is a single feature which has got two different manifestations as you look at it. Right?
Yes, sir.
Okay.
Probably
So
because dual comes from the word two. Is that something to do with that? I don't know. I'm just
yeah.
talking about this
Exactly.
terminology.
Exactly. That is what I was talking about. From beginning only, we have been thinking that it has to be either discrete or continuous. Right? Later on, we identified that, okay, if it is discrete, it is matter, or if it's a matter, it is discrete. And if it is energy or force, it is basically continuous. That was the idea. It was Max Planck who told initially that, okay, your energy also is discrete and it has to be discrete. And experimentally, photoelectric effect and other things could be done. In fact, when Planck actually explained this thing, he was doing mathematics only. He was basically an expert in thermodynamics, Max Planck, right? But he was trying to explain what happens in the black body radiation so that you are getting this kind of pattern, and Rayleigh-Jean's law was unable to explain that thing. So his idea was that can I at least handle this thing mathematically? He did it mathematically only, right? And that is why, otherwise, why he will give the name H to his Planck constant? In his whole name, H does not come in,
Yes.
right?
Yes.
Because this
So it
is
was
my own
just
understanding. I don't know whether I have not seen it written anywhere, but I have told this to many people as well, that H might be there because if you talk about our numerical methods, what is this very smallest increment we are talking about as far as symbol is concerned? We say it is H. For example, in your Newton forward interpolation, you are saying that your X is equal to X or X1 is equal to X0 plus H. So that H was basically a kind of increment knowing symbol. It is increment only. So he also told that H is an increment in the energy. If I have this much energy, then the next energy available for that radiation or that frequency is this much. So he in himself was not also very serious about that idea. He himself told that it's a mathematical practice, right? But later on, it was identified that no, it is not just mathematical. It is the thing which is happening in nature, right? So see how do we evolve? How do we evolve into understanding certain thing that makes the science, right? And this duality word itself is coming just because of our mindset that it has to be only and only wave or particle, nothing else. But whenever we are having some two things, we call it duality. It can be a multiple thing also. We don't know. We might not have seen a particular aspect of matter at all till now. We don't know.
Yes.
Right?
Yes, sir, I got it. Thank you.
Okay. Yeah. So I'll just complete this thing and then we'll start discussing. Actually, discussion is the thing that is required in such interactions, right? Presentation is just to trigger that discussion. So if you talk about the particle zoo, as it was called, now if you ask Vinod Kumar, he will say that it is not particle zoo. It is basically a particle sanctuary, because sanctuary is the place where you are basically handling them, right? Zoo is a different word altogether. Okay, so if you talk about these things, we came to know about here I'll have to change the color. Okay, we came to know about electron, right? After a long time, we found the proton. Okay, after again a long time, we found neutron, then positron. After the Dirac postulated that thing, then muons and many other things, right? So you were having lot many types of particles. Okay, then these were again another zoo of particles. But basic idea was that in 1964, it was basically Gell-Mann and Niemann who basically proposed that, okay, if you can make a Mendeleev's periodic table for all the chemical elements that you see, right? Why can't we make a kind of table or kind of chart which can explain what are these particles that are seen in the experiments? Okay, and then they came up with something called standard model, right? But this is not the standard model that they came up with initially. They came up with only this UDSC, right? Or even C was a postulated thing for them. C was not experimentally identified in 1964. C basically came in existence in 1974. Okay, so they were having only up and down. U and D normally makes all the matter that you see. U and D and electron, basically. Only these three make all the matter that we see around us. Okay, so UD, if you say it is a proton, UDD will be a neutron. Okay, so there were so many concepts behind all these things, but they identified that, okay, if you arrange them in certain ways, I have not actually shown those arrangements here. They are basically called octets and decuplates, nonates, and all those things, right? So if you arrange them in a certain way using group theoretical concepts, then you can tell that, okay, your standard model is basically comprising, or all the particles that you see around are comprising of these particles, right? So you have got up quark, down quark, charm, strange, top, bottom. They are named like that only. Okay, this gluon is basically your field particle, you can say, or carrier, gauge boson, or carrier of the force. Okay, this is particularly for strong force. If you talk about these quarks, they interact via something called gluons. Even gluons also interact with among themselves. For example, if you have got two photons, they don't interact with each other. They will simply pass through, right? But if you talk about a gluon, they will interact with each other. That means two gluons can attract each other. There is no repulsion as far as strong force is concerned, right? As far as gravity is concerned, again, there is no repulsion. And we don't know why is it so. Okay, so if you talk about the forces, your strongest force is strong force. If you talk about the forces, the weakest force is also the gravitational force. Both of them have got only attractive counterpart. There is nothing called anti-gravity, or there is nothing called strong repulsion. They are always attractive. Okay, electromagnetism as well as electroweak, both are having both the counterparts. Okay, but your electroweak, if you say weak interaction, that weak interactions are basically having this W and Z bosons, right? This gamma is for electromagnetic, this gluon is for the strong force. And the question was that if you see this photon, what is the rest mass? Zero. If you see gluon, what is the rest mass? Zero. If you see Z bosons and W boson, your masses, you can see they were tremendous. If you talk about, say, proton, the mass of proton is approximately 1 GeV. To be precise, 938 MeV, right? Neutron is also similar mass. But if you see here, W and Z bosons, they are very, very massive, if you see carefully. Now, when these are this much massive, the question was why they are having so much of mass when they are carriers. And you are talking about these bosons being exchanged when there is something called, say, for example, beta decay happening. When beta decay happens, you are having W boson involved in that. Now, in beta decay, what is happening is a proton is converted into neutron and neutron is converted into proton if you talk about inverse beta decay. So, basic idea is that how a carrier can be so much massive with compared to even the initial and final particles. Then that thing was explained using something known as Higgs mechanism, right? And that Higgs particle was experimentally found in 2012, as we know it, okay, in LHC. So the basic idea is that as far as particle physics is concerned, the developments have gone first in theory and then they were identified experimentally. In most of the sciences, experimentally something was identified and then it was explained theoretically. In particle physics, you are proposing in theory. This charm quark was proposed in 1964 only, experimentally identified in 74. In uh, in 70s only, it was proposed that there has to be 3 generations of quarks. That at that time, this top and bottom were not known, right? But experimentally, they were found to be happening or to be existing. So same happened with the leptons as well. So theory was going much ahead of experiment in all these things. But nowadays, if you see carefully, whatever experimental results that we are getting, it is very, very difficult to reproduce those experimental results using the theory that we know today. So practically speaking, we really do not know exactly how it is behaving at subnuclear level. That is the issue. And that is where we are standing right now. Okay. If you see carefully, if you go on changing the levels of energy, right? For example, if you talk about few electron volts, you are talking about energies which are corresponding to some transitions in atoms. If you talk about kilo electron volt, you are talking about again electromagnetic interactions, means you will be expecting X-rays to come out of those systems and all. If you talk about MeV, you are going to subnuclear thing. If you are going to GeV, you are probably going to even further level, right? And you will be going up to, say, sub proton or sub neutron level. Okay. Whenever you go beyond one level in 10 to the power, then the physics is changing. And the moment you say that you are going inside the protons and neutrons, what exactly is happening there, we cannot visualize. The reason is that obviously there the things that are working are basically your quantum realm. So it is basically quantum mechanics which is working there. And unfortunately, our thought process is classical always. So we can explain the quantum mechanics only using the analogies that we see in our what you can say uh, classical world. But the problem is that in classical world, you don't have any counterpart which can be explaining many of the quantum mechanical effects, right? Okay. So up to this point, I just wanted to tell that, okay, it has reached up to this level. And of course, as we discussed just now, it is not these particles which we talk about when it comes to particle physics. We talk about something known as quantum field theory, right? What is quantum field theory? You are now proposing, or you have proposed. Basically, quantum theory as such, if you talk about, it started in 1928 only when Dirac started it, right? Dirac talked about the Dirac electron sea, if you recall. Okay. That sea was basically a field as such, right? And if you try to explain your annihilation and uh, creation of particles, then in terms of field theory only you can explain that thing. For example, if you talk about Schrodinger equation, we typically say that, okay, H psi is equal to E psi. This is how we talk about, right? This is your Hamiltonian, this is the energy. Now, this is valid if and only if your psi corresponds to a particle, basically. If the particle was already existing, then only you can use this thing. The moment you say that, okay, can I handle the creation and annihilation of particles from nothing using Schrodinger equation? The answer is no. And that is where this Dirac comes in picture. Okay. And that is where your quantum field theory concept starts. Basically, quantum field theory is again a very vast subject, mathematically quite challenging, you can say. But one part, quantum electrodynamics, right? QCD is quantum chromodynamics, right? C means chromo. So this basically is talking about the color part. Chromo means color in the quark model, you can say. Okay. QED is well understood. Whatever QED tells you experimentally, every single thing is verified, and it works perfectly all right. QED was basically due to so many people, but one of the major contributor to that thing was again Feynman, in whose name we are right now talking. Okay. So no doubt QED was not directly given by him, but he was the person who did it in a large way, you can say. In rest of the cases, it was very much complicated. He made it a bit simpler, but of course, simpler does not mean that it is simpler than any other field. Huh? Okay, so this quantum field theory says that all you have are different fields, and whatever particle you are talking about, they are just excitation in those fields. So, for example, if we talk about this thing, how many different fields we have? So we have got, say, 6 quarks. Okay, so we have got 6 quark fields. Then we have got 6 leptons. So 6 leptons fields will be different. We have got these 4 mesons, right? Bosons, gauge bosons or field carriers. We have got Higgs bosons. All of them have got their own field. Okay. Another thing, we say that your quarks are basically having another feature called color, and your gluons are also basically having a feature called charge, color charge, or color charge means that color only. But gluons are made up of color and anti-color. Gluons use color and anti-color. Quarks are having only color, anti-quarks will have only anti-color. But the moment you say that you are talking about a proton or a neutron, right? For example, you say that UUD, this is basically a proton. So here, this will be a red, this will be a green, this will be a blue, right? So this quark is different than this quark in color, than this quark. And you can explain that thing because a quark, suppose if you have got a baryon, which is say UUU, definitely up quark, up quark, up quark, they are all basically fermions, right? So you can say that this has got spin half, this has got spin minus half. What about this one? So you cannot have a system in which all of this can work. Then they must have some property which is different. And that some property was proposed to be color. And that color is this thing. Okay. Of course, this has nothing to do with our real world colors. Huh? Just keep in mind. These colors are different than our real world color. They are not colors that way. Just name is given color. But particle physics is like that only. We use the word charm, beauty, top, bottom, up, down, right? It can be, instead of up, down, it can be left, right also. But they named it up, down. So it works like that. Nothing else. Okay. So basic idea is that your color hypothesis came due to certain requirements which was there existing due to, say, exclusion principle and so on. Okay. So basic idea is that whatever you experimentally observe, try to incorporate in your theory, try to change your theory in such a way that you can explain those things. Now, if you think that everything is in terms of fields, suppose if you have got a photon, that means it's an excitation in the photon field. If you have got an electron, it is excitation in the electron field. That's it. So all fields are existing everywhere. Just like you might be remembering, there was a concept called ether. Do you recall? Ether.
Yes.
Yeah. What was ether concept? It was stating that, okay, if light has to come from sun to earth, for example, then it was understood that any kind of wave will require some kind of medium to propagate, right? So it was told that, okay, ether is happening everywhere. Many people consider that your this quantum fields are just like this ether only. But it was proven that ether does not exist, and it is proven that fields do exist. And the latest example is Higgs boson itself, okay, which was experimentally identified. But one has to understand, what we can measure is only excitation in the field. We cannot measure the field itself, right? So field is existing everywhere. Right now that you have got all the fields available, right? For example, you have got a red quark field, red U, green U, and blue U, for example. So you have got three different fields. Those three fields interacting with each other gives rise to some UUU baryon. Or if it is D, it will be UUD baryon, or maybe a proton, something like that. Okay. So whenever you say that interactions are happening in the field, and then there are some excitations, those excitations are the particles. And we are talking about particles because experimentally we can see these particles only. Again, they are not directly coming. They also come through some indirect means, right? For example, we have never seen atoms, we have never seen molecules, but we can very certainly tell about their shapes and other things as we understand them. Practically, we don't know whether they are there like that or not. Okay. Yeah. Now, if you have any question or discussion, then we can, or points we can discuss. This was just to trigger the discussion.
Sir, can you shortly tell us what is the quantum field?
Quantum field means that is something which is happening everywhere. See, to answer that particular question, the very first question is, what is the field itself? Chalo, anybody? What is the field? Forget about quantum word right now. Just field. Say for example, I have got a field. For example, in this region, I have got a field, right? This is a region in which I have defined some particular physical quantity or attribute, right? Suppose at this particular point, my field has got just a value. For example, I am talking about temperature in this room. Okay. At a particular point, I know the temperature of that particular point. Okay. And it can be changing throughout the room. It can be anything. So if you say that I'm talking about the field, here at this particular point, I can define what is my temperature. So I will call it point T1, I'll call it point T2 and so on. But if you talk specifically, you are talking about a scalar field. Scalar field means it does not require any temperature, direction. Suppose if it's a temperature, how can you say that there is a direction to the temperature? No. But at the same time, for example, instead of this field, suppose if I say that I am having an electric field, right? Now, if it is electric field in this region, definitely I have to define in which direction the field is. So that will basically give rise to something called vector field, right? So basically it is some particular quantity in that particular region, right, which has got some magnitude. In some cases it will have direction, in some cases it will have even tensor also. There can be tensor fields as well, right? For example, if you have got some particle here which is basically undergoing some additional stress because of some external field, right, then it will have something like stress tensor kind of field. So at this particular point, if I want to explain this particular particle or this particular point, I will have a value, I will have a direction. So this is basically a vector field, scalar field, but this is in space. Now, when you say it is quantum field, for example, now quantum field does not have the features directly like means direction and other things. in quantum field, these attributes which we are talking about in normal physical world, what we talk about is direction and magnitude. Okay, even when you talk about tensor, again it is direction and magnitude only. You have got multiple components coming in when it is tensor. For example, it's a rank 2 tensor, you have got 9 components. Okay, so suppose if I talk about quantum field, what are the attributes a quantum field will have? So you will say that, okay, it can have spin, right? It can have charge, it can have say chirality, or you can say helicity, right? Many things. Helicity normally belongs to a particle, but okay, because we are talking about quantum field, you can talk like that. So many things are there: orbital angular momentum, spin angular momentum, right? Magnetic quantum number. Many things can be associated with a particular point only, right? But that is a point which is happening in a particular field. So an excitation in that field will have all these features as such, right? So quantum field is basically just like field only, our regular field only, but it has got the attributes which are quantum mechanical in nature. For example, spin is a quantum mechanical concept, right? No doubt, everybody knows that your electron does not spin on its own axis, just like Earth is doing. Then, right? Is it clear?
Yes, sir. Thank you.
Yeah. Anything else? And I just recall one. I'll just try to find out. I have one slide which was basically suggested by one of a known person. I don't know whether you know of Sudhir Raniwala or not, right? Sudhir Raniwala basically had one particular example, and I like that example, so I'm just trying to quote that thing here. If I can. Okay. So as far as your particle physics questions are concerned, or particle physics experiments are concerned, there is a saying. For example, let me. Yeah, can you see the screen? I have changed the slide actually.
Yes, sir.
Okay.
Yes, sir.
Now, yeah. This is an example basically from Sudhir Raniwala. Again, this is something which I'm just showing you, right? It is not my own idea, but I like this thing. Now, suppose this is a simple question. Can you tell what might have happened here? Anybody? There is no other input. There is no other clue, right?
So an airplane is moving in the sky.
Okay. And it is going maybe on top right. Fine. So
Yeah.
you could suggest this thing, right? You could tell. Did you see airplane going? Actually?
No, sir.
Yeah, you did not see the airplane going, but at the same time, you already knew that if airplane has gone, then we must have this kind of tracks. There is no other
Yes.
way of finding those kind of tracks in sky. Okay.
Hmm.
So
Yes,
there
sir.
was already some input with you. Your particle physics problems or particle physics experiment work in this way only. For example, after the interaction has happened, for example, if you are talking about LHC, you have got a proton bunch coming from this side, you have got another proton bunch coming from this side, and when they collide with each other, whatever debris come out, from those debris, you are trying to understand what was the interaction happening when they collided, right? And it is not this simple. This was a simple case. On first attempt only, you could identify that exactly this is the problem, right? Now, I am
Yes, sir.
asking you another question, right? You could guess it right. There was no question about what was the thing. Now, can you tell what might have happened here? इसने ऐसा क्या देख लिया होगा कि ऐसा एक्सप्रेशन आ गया? What might have happened here? Now you are thinking of many answers, right? And probably you might not want to tell those answers here. किसी के दिमाग में ये भी आया होगा कि भूत भूत देख लिया होगा, लेकिन फिजिक्स का क्लास चल रहा है, भूत की बात कहाँ से करेंगे, right? But the question is, you get particle physics data like this, not like that plane. You have to identify what might have happened. There are so many other circumstantial evidences where you will tell that, okay, because whenever this fellow gets a kind of attack of something, hysteria or something, he gets this kind of face, right? Then definitely you can tell that, oh, he has not seen any ghost or anything. He does this thing because he has got a medical problem, because of that thing it is happening. Okay, so this is the thing, right? So whenever you see that a particular outcome is coming from a particle physics experiment, there are so many things which might have happened inside, and you have to bifurcate them in such a way that you have to break them apart and identify that this might have happened. And that's why you talk about probabilities in quantum mechanics. In principle, you are talking about probabilities whenever you try to predict anything, right? And in quantum mechanics, whenever we use those things, we are basically trying to predict something. Mechanics means I have found some kind of mathematical formulation. I can use that mathematical formulation to explain something if certain physical experimental conditions come up. Right? Now, any question? I just recall that this particular example can
Hello?
be a good one to share.
Hello.
Yes.
I have read that many scientists are trying to prove ether is the medium, that is the final medium, that why they want to prove that ether is the final thought.
See, first thing is that very early
they are putting many efforts to prove that the ether is the medium is there.
Yeah. See, the very first time ether was introduced, it was basically believed that any wave will require some kind of medium to travel, right? And in space there is vacuum. So how electromagnetic radiation is coming from everywhere to Earth, or from here to everywhere for that matter. So to explain that thing, they gave a concept of ether. Later on, Michelson-Morley experiment was done, right? And then in that experiment, they tried to prove that if it is so, then means they could show that the light is traveling in the same, what you can say, same speed in all directions, and everything was like that. And exact details I don't have, but they explained that if certain features are observed, then only the ether is there, and those features were absent in their experiment. Those shifts in the measurements are absent. But after that, this was basically, so the idea of ether was ruled out at that time. I am talking about 1920s. Okay. Later on, somebody identified that their measurement process was having some uncertainty, and that, or some standard deviation, you can say, and that standard deviation was more than the shift they were claiming. So ultimately, Michelson-Morley experiment, if you see, it did not prove that ether is not there in principle. Okay, but the thing is that whenever there is any shocking or surprising, fascinating announcement is there, people will be very eager to put those things. But later on, if it works out that okay, it's not working, then people don't see those things. So if you see literature properly, that Michelson-Morley experiment itself did not prove that ether does not exist. Number one. Number two, right now, why people are thinking this way? Because people are already thinking this thing, that all these quantum fields, these fields are present everywhere in the universe throughout. For every single particle, there is a single quantum field, because that is the only way you can explain why electron on moon is exactly same as electron in, say, some Andromeda galaxy, for example. They can be exactly identical if and only if they are part of the same thing, or they are the same thing for that matter, right? If electron is a particle, then there must be a chance that the electron on moon, the electron on sun, the electron on, say, Mars, the electron in just near a black hole, they must be a little different if they are separate particles. But it is observed continuously from every single experiment that all electrons are absolutely identical, all protons are absolutely identical, all the things that you see are absolutely identical as far as your basic elements of matter are concerned. That is why the concept of field basically holds that thing. And here you don't need to talk about that duality thing also. चाहिए ही नहीं, duality क्यों चाहिए आपका explain करने के लिए? You are already telling that it is a field, and whatever particles you are talking about is just excitation in that field, nothing else, right? And another important thing, I don't know whether you are aware of this thing or not, but your vacuum is the most notorious thing which that can happen. Vacuum is something from where you can generate anything, right? For example, I can generate a CC bar from vacuum, provided that I abide by this rule: delta E, delta T has to be less or equal to h bar by 2. If I follow this thing, if I want to take some energy from vacuum for delta T time, and if my delta E into delta T is less than h bar by 2, right? Then I can take that energy, I can convert that energy into particle and antiparticle, and then it will be existing only for a small time, and then it will annihilate again, and it will again become vacuum or something like that. So from vacuum, you are creating anything. And that is possible if and only if you have got a quantum field concept or field concept. Yes.
Sir, these are the Fadipopov ghosts you are talking about? Or the charmed quarks?
I do not hear you.
Sir, this CC bar you are talking, am I audible now, sir?
Yeah. CC bar is just an example. It can be anything. Any particle, antiparticle pair can be generated from vacuum, provided certain conditions.
Okay. Yeah. That is the condition for the virtual particles that you are saying. Means this condition, whatever you have written, is the condition for what?
Yeah. They will quickly come into existence and annihilate, right? But at the same time, no. But at the same time, virtual particle does not mean that they will not be ever seen. If they can club, for example, suppose I have got a CC bar, okay, and that CC bar is getting annihilated, right? Or it is getting converted into, say, CU bar and C bar U, for example. So what I have done is I have taken this UU bar from energy somewhere. So that energy is converted into UU bar, and I am getting CU bar and C bar U as an output, right? So that U bar which I generated from my energy is still there with me. They are not virtual. But suppose if I am generating something from vacuum, then it is virtual.
Yes, sir. That was what exactly.
If it is generated from energy, it is not virtual. It is still there at the end product.
Yes, sir. Means I basically thought that you are talking about the Fadipopov ghosts over here, CC bar. Hence, I was just a bit
No.
curious. Okay.
This is just I was just talking about what can you do from vacuum. Vacuum is basically a most notorious thing that you can have in field theory, rather in every field for that matter.
Sir, is that
Yeah, I can hear.
hello?
हाँ बोलिए.
Sir, is it the same that vacuum state we define in quantum optics?
That I have to check. In quantum optics, what is vacuum state? I don't know. but it might be the same. I don't. I need to see the context in which you are talking about.
Excuse me,
Because
sir.
quantum optics, I don't have
My,
much idea. I have some idea about regular optics, classical optics.
So how do we define this vacuum in the sense of physics?
Pardon?
How do we define this vacuum?
Vacuum, basically, see, normally, how do you define zero, for example? Zero means you are saying that, okay, I have got some particular property which is not changing with time and it is steady as such, right? And it is at the, it is neither negative nor positive, there is nothing. So we call it vacuum, right? Or we call it zero. Similarly, this vacuum is basically, you are having, say, for example, so many quantum fields in a given region, right? For example, uh, you are
So you
having
you
n
mean the
number of
concept?
fields here. If there is no excitation in this field, then all those fields basically make vacuum only. But your vacuum has got whatever particles we saw just now. If you really count, there are 37 different fields as of today. Later on, if you find something new, they also may.
Yeah, kind of.
Somebody is
I think somebody. Yes, sir. Yes. Wait a minute. Yes. Now I think, sir.
Yeah, yeah. Sir, can we define vacuum like the lowest available potential energy in a region, or the lowest potential energy a field can have? Means provided we have this, the when we talk about the quantum fields, okay, this is the lowest energy, but still the particles are having some amount of kinetic energy. The lowest state of their fields. This.
સર તમે મ્યુટ છો.
Sir, you can unmute yourself, and I think so. I have made a mute all, so that's why.
Now I am audible?
Yes, sir.
Okay. See, this is basically vacuum expectation value. There is a word, there is a term here. Normally, this comes in when you try to explain something known as Higgs mechanism, right? So, suppose I have got a field. Now that field is basically having some kind of continuous variations, vibrations. So, what is the average value that we are talking about, right? If the average value is near zero, then you will say that it is your vacuum expectation value. But in some cases, for example, if you talk about, say, Higgs field, your VeV is non-zero, right? So depending on which particular particle you are talking about or which particular field you are talking about, your vacuum expectation value can be different. And the vacuum expectation value of Higgs field is always non-zero, always non-zero. So whenever a particle interacts with that Higgs field, it is basically giving rise to some kind of change in its own mass. And that's why your Higgs, basically, we say that Higgs is giving mass to all the particles. But in principle, as of the thing that we know today, Higgs particle or Higgs field is not giving masses directly to these fermions, right? It is giving mass to those force carriers, and ultimately then it goes to the fermions.
So, sir, can we
Yeah,
define vacuum as the lowest potential available to a particle, or potential energy available to a particle, or as field?
yes,
In that
yes,
context?
we can. But again, this again I'm saying, whenever we talk about this field, then excitations are automatically telling that it is not at the zero energy.
Yes.
right?
But these excitations
That
are very
non-zero
small if we
energy, that
compare
non-zero
to.
energy is giving rise to the mass of the particle. Again, there
Yes,
comes your
that comes.
mass energy
Yes.
equivalence.
Yes, that comes directly, means if we look at the Higgs mechanism, the mass is actually the coupling constant between the interactions.
Correct. So basically, that is the place where you directly see that mass is energy and energy is mass.
Yes. Yes.
Yeah. Any other question?
Excuse me, sir.
Yeah.
Yeah. So, sir, when we say that the electron on the Earth and electron on somewhere else in the universe, these both are same, and they are same that we know.
Right. Yeah.
So, is it true that the field that we are talking about, the quantum field, it is continuous or it is discrete?
Fields are never continuous or discrete. See, for example, if
Okay.
I talk about, when you talk about, say, space, is space discrete or continuous?
Uh,
Space. Is time discrete
and
or continuous? See, when it comes to computing something, we have to make it discrete, right? We have to talk about some kind of time step or some kind of space step. Suppose if I talk
right.
about what is the space, is it continuous or discrete? So your answer is definitely space is continuous as such, because there is no point in space where you cannot assign any number to it, right? You can tell that, okay, this
Right.
is the coordinate of this particular point. It is absolutely continuous. And field is nothing but some particular property or some particular feature which has got certain values at every point given in space. So if space is continuous, fields are continuous. If space is non-continuous, fields are also non-continuous.
Okay.
Did I confuse you more or what?
No, sir. It is a bit clear. And I have another question, sir. So when we
Yeah,
say that the quantization of the field gives us the particles,
not quantization, excitation in that.
excitation. So is
Yeah.
it true for all the particles?
Yes, it is true for all the particles, all the photons that you see around you, all the gluons, all the quarks, every single thing that you have.
Okay.
So
And see,
if
if you see quantum field theory, then there are so many. See, question is, sometimes people say that, okay, there was a question why Earth is rotating. There was a question like that, okay, why Earth is rotating. So best answer was because nobody had stopped it so far, right? That is the best answer. But actually speaking, why everything is rotating? Well, every damn thing is rotating, including electrons and your solar system and galaxies, and everything is
Yes.
rotating. Why everything is
Yes.
rotating? It might be explained only properly through your uh, quantum field theory concepts only, right? Otherwise, you can think of a situation. For example, you have seen that your visible universe is how much big, right? I don't recall the numbers right now, but it will have some finite distance in light years, of course, right?
Yes.
And sometimes you see the what you can say, sometimes you see in newspapers and in research papers that they've identified an explosion which was, say, this many million light years away. Okay. So
Yes.
basically,
Yes.
of course, whenever you are looking at space, you are looking back in time. That is always there, right?
Yes.
But
True. Yes.
at the same time, uh, if universe is continuously expanding and it is getting accelerated also, how that light reached you? If you try to explain those things properly, if you try to explain even up to some extent, I'm not sure whether entanglement has something to do with this or not, but your field theory only can answer many questions like this. The moment you say that, okay, there was something called big bang, and that big bang, everything exploded from a single point, then at what speed they must have traveled initially so that your galaxy is this much big now, or your universe is this much big now, right? and it is still accelerated. So there are many things. So for example, when it comes to field theory, then only probably after some other incorporation with general relativity and other things, you can talk about this dark matter and dark energy in a later stage. Right now, still we are not having any idea about what exactly to do with that.
Right.
Okay. Yeah.
Yes,
Any
sir.
other?
Yeah.
Anything else? See, the basic thing is that in this particular chapter, we can only give rise to certain basic discussion. There is no direct application stuff here, right? So we are just
Yes.
trying to explore the things.
So maybe the person who asked the question, actually
Yeah.
he wanted to listen about why the word quantization is used. This means quantum field theory. So there is a classical field theory, then there is a quantum field theory. So
No,
maybe
that's what I'm saying.
he wanted to know why this quantum word is
Fine,
used.
fine. Because see, that's what I was telling in the last slide. If you see here, when you say that you are having a field, right? Our normal classical field basically will have some value at every given point in space. Okay. You are having the properties which are defined only in quantum mechanics in these fields. That is why you call them quantum field theory. That's it. Because every point will have some definition, some property. See how electron will have spin, because its field has got spin inbuilt in the in its construction, you can say, or existence, whatever it is.
As you said that this excitation of the field is the uh, generation of the particle, right? So if it is continuous, so then we can produce all kind of masses. So that's why maybe there are specific rules like this.
No.
That is
Of course they are there. Of course they are there. Every field will have its own specific properties. It is not like,
yeah.
the
Yeah.
electron
So
field is
they
definitely
they
different
follow
from
they
proton field.
yeah, they follow certain rules. In
Of
that
course.
they quantize. They
Correct.
can excite. So
Correct.
that's why we use quantum field.
Yes. Every single field has got its own unique properties.
Yeah. So is there any connection to this uh, Higgs field and this ether? Means the concept of ether is
No,
gone,
no,
right?
yeah,
The concept of ether is gone.
it
But
is very interesting
it's
question.
still is yeah. It's still I'm thinking about this Higgs field like
Yes.
ether.
There are people who strongly believe that Higgs is nothing but that ether that people used to talk about. There are many people who strongly believe so, right? And it is a debatable question whether your Higgs field is the original ether that we were talking about or not. But that ether was not having any other property than allowing the disturbances to travel through. That's it. But here, this has got a property which can give masses to the mediators. That is the thing.
Sir,
It might
in
be. It
that
might be. I have seen papers where people are listing Higgs as ether of modern particle physics or something like that. Now, there are articles like that. But
sir,
it has got
I have a
quantum
question.
properties. Earlier, ether, when we were talking about, it was basically like fluid kind of thing. Look, visually.
So in the field theory, what I don't know much about the particle. So what is the interaction between this Higgs field and the electromagnetic field? So is there interaction?
Higgs field and
Electromagnetic waves.
see, Again the same thing. You have got electromagnetic waves, okay, electromagnetic field. You have got Higgs field as well, for example. Now electromagnetic field has got excitations, you call them photons. It does not actually interact with the Higgs field at all, so your photon does not have any mass. Okay, they are all coexisting, interwoven kind of thing. Every single point in space has got say 37 fields available, and each field will have some value there. Many of the cases it will be zero, right? See, basic thing is that fields are there, separate fields are there for separate particles, but all of them are existing in the same space.
Right.
So definitely they can interact with each other in just like two other fields are interacting with each other. It is like suppose you have got say you the people give this particular example. You have got a guitar string, and if you pluck it, right? So at what point, at what force, with what force you are plucking it, it will create some vibrations, right? The same thing happens when you are talking about interaction with these fields. No doubt, it's a very classical kind of analogy, and quantum mechanically, what happens at that level, people cannot directly visualize. We cannot directly visualize.
Okay.
Excuse me,
Sir,
sir.
I
I
have
have
a
another
question.
question.
Yeah, yeah.
Hello.
Yes.
Yeah, sir. Yeah. So, sir, when we say that the excitations of the field creates the particles,
Mm.
so how these excitations are created? I mean, is it a spontaneous process, or I mean, how it
See,
is to be interpreted?
basically, all the masses that you generate are happening because of something known as symmetry breaking,
Okay.
right? In fact, it itself is a uh, big topic in itself. But I'll just show you one basic uh, illustration. I'll say your Higgs field
Yes.
is basically looking something like this. It's like Mexican hat, I think, right?
Okay.
So, for
Yes.
example, if you have got a particle here, okay, if you have got a particle here, now the question is that as such the system is completely symmetric. Okay, if I draw a line here, okay, the system is completely symmetric.
Right.
Now, by chance, if some perturbation comes in, what will happen? This has got a probability to fall on this side. It has got a probability to fall on this side as well. Right now, as
Right.
such, it is in the lowest possible energy state as far as this potential is concerned. But is it lowest? No, lowest points are this and this. So after a perturbation, this particular particle might fall either here or it might fall on this side. The moment it falls here, it is basically creating a kind of asymmetry in the system. And that says that, okay, you have gained some energy or something from the Higgs field, and so your particle is gaining any mass because of this asymmetry.
Okay.
So it is interaction of the particles. Again, these particles are also excitation in their own field,
Right.
right? This concept is called symmetry breaking. Only symmetry breaking can give rise to mass. And whatever mass that we see around us, that mass is, again I'm saying, that mass is because of the interaction of that particular particle's field with the Higgs field,
Higgs field.
ultimately. It is, see, it is like normally we say that you have got matter and antimatter. From vacuum, if you generate, you have got matter as well as antimatter. Why do we have so much matter around us right now? Because of this kind of symmetry breaking only, nothing else. But it happens on a very different scale,
Okay.
right? Just like if I talk about that particular example which Feynman gives, you know how a chess pieces will move, right? There are certain rules for
Right.
every piece, but you don't know how a particular player will play his next step. He knows all
Right.
the rules. The nature behaves in the same way. We can only see and generalize certain things. Even suppose when you talk about particle physics, even today there are n number of problems where we don't know how to explain them theoretically, and experimentally they are seen.
Yes.
Okay? For example, if you see the history of particle physics in that sense, right? We have always seen that there is something called weak decays. They always challenge your physics knowledge, always. They started with discovery of kaons that I discussed about, that I listed in that 1947, right? You have particles which are generated through strong interaction, but they decay with a lifetime of 10 to the power minus 8, 10 to the power minus 12 second. They are very long lifetime when you compare with strong decays, which are basically happening at 10 to the power minus 23 seconds. So why it is happening? Because they had something called strange quarks in them. Okay. And that's why that quark was named strange, because it was behaving strangely. Later on, when you say that, okay, you are having certain issues as far as the charge parity violation is concerned, or parity is violated or not, well, weak decays are violating parity. Then somebody told that, okay, if you combine charge and parity, they may not do that thing. But again, it was found in kaon decays that there were some long-lived and short-lived kaons. And again, weak decays were the culprit to tell you that, okay, CP violation is there. Now, CPT is considered to be absolute symmetry of nature, where T means you are talking about time reversal. I have got one particular event happening. If I reverse that tape in video, can I tell that whether it is a reverse or whether it is forward? For example, if somebody is walking and if I take a video, you can tell that, okay, this person can walk even backward as well, right? So you can say that, okay, both the events are as such possible. So it is understood that all the events can be having some time reversal symmetry. But weak decays are still considered that, okay, they might even break that time reversal as well, because they have to obey the absolute CPT symmetry. But see, all these things are basically part of hardcore particle physics classes. So we won't be discussing
Yes.
here. It may not be interesting
Yes.
to everyone.
Yes. Yes.
Sir, I have a question.
Yeah.
Sir, as we were talking about ether and Higgs, that some people are considering Higgs as the ether. Is it not more feasible to consider the Goldstone boson as ether? Because we know that Goldstone bosons can interact with the photons, especially in the Stuckelberg formalism of Roca theory, and then they restore the gauge invariance and everything. So, means just a curiosity from me, means
Yeah,
while
I am not aware of any answer in this particular question. I need to read that thing, because Goldstone boson, uh, can you relate it directly to Higgs? I don't know.
no, means we know that the diagram you have shown is that when we are considering this kind of motion, but there is another also this kind of motion which will have the Goldstone boson. So when we talk about Higgs, is that the Goldstone bosons are getting absorbed and then we are getting the Higgs. That is the formal theory what we have studied. But if you look at the Stuckelberg formalism, there is a coupling, derivative coupling of the scalar field phi with the mu field, and
Okay.
that is exactly a Goldstone boson, because that particle scalar field phi is massless in nature, so that does not contribute to any mass change of the field if we are considering a massive vector field in the abelian case. So that's what Proca is all about. Now, Stuckelberg formalism was that this when Proca defined that Lagrangian, the Lagrangian was found to be gauge invariant, gauge variant. So Stuckelberg used this transformation, and then he found out, okay, we can have this. So my question
Right.
is particularly this: that in that scenario, can the
Hmm.
Goldstone boson be acting like ether?
Mm, I don't know.
Okay, sir. I even don't know whether it is
I
a valid
I'll have,
question or not. It's just out of
that
curiosity it
also I
came to
don't
my
know.
mind.
Yeah, that also I don't know. That's why I told you. I'll
Okay.
try to explore this thing and come back to you. Not an issue.
Okay.
Right
Okay.
now, I
Thank you.
don't have anything. Nothing comes to my mind when we discuss this.
Okay. Okay. Okay, sir.
Yes. Any other question? Okay. On a lighter note, let us have this thing. In fact, yeah. Have you seen this particular problem? This again comes from that idea that whatever we see around us, okay, this is basically to be given to undergraduate students as an example of what is the way of your thinking when it comes to any particular problem or something like that. This is a very famous example. I don't know whether you are aware of this thing or not. Have you seen this thing anytime? Any example
No.
related to a General Motor Pontiac model? See, this is
No,
a very
no,
famous
sir.
one. I don't know whether you have seen this or not. Has anybody seen this particular example?
No, sir.
Okay, then it will be more interesting for you. See, the basic idea is that how a physics person or how a science person should think, right? The gist of this thing is this much only, that on one particular day, General Motor got an email, right? That I have bought a new Pontiac car, which your company has made, and my car does not like ice cream, vanilla ice cream particularly, right? So obviously that kind of email will be ignored by any technical person. So that happened 2 times. Okay, this fellow is writing that my car does not like vanilla ice cream. So General Motor is a company which will basically try to take care of their customers. So one engineer was assigned. Let go and see what is he saying. He told that okay, whenever our family has a tradition that whenever we are done with our dinner, we will go to a particular store and then we will bring ice cream, come back, and we will eat that ice cream together at home. That is our tradition, home tradition, okay, family tradition. Now, when we go to a particular shop only, right? Whenever we go there, and if we buy vanilla ice cream, the car will not start. Okay, it will take a lot of time to start. And whenever there is any other ice cream, it will immediately start. So this was a problem. Now, definitely that engineer thought that how is it possible? Means what ice cream has to do anything with that? He told that, okay, I would like to experimentally check what you are saying. He told, okay, you come along with us. Now that fellow went to the ice cream shop with this family man, right? And he told that, okay, today you bring strawberry ice cream. So that fellow brought strawberry ice cream. The car started immediately and they came back. Next day he went and he told that now today you buy vanilla ice cream. So that vanilla ice cream that person bought, right? And the car did not start. The engineer is seeing this thing, right? Now that happened 2-3 times. Later, whenever there is any other flavor, it will be starting normally. Whenever there is vanilla, there will be a problem. So now this fellow was basically an engineer, right? So he started noting down all the parameters that, okay, this much was the fuel in my car, right? It took this much time to start from home and to reach the shop and so on.
Yes.
So, yes.
No, no,
Hello.
no, no, sir.
Yeah. So he was basic. He tried to note down every damn thing. Later on, he found that it is not the vanilla ice cream. It is the time taken for the person to come back after taking the ice cream from the shop. That shop was basically very famous for vanilla ice cream. So they had kept a separate counter for vanilla ice cream. So whenever this fellow goes to buy vanilla ice cream, he will very quickly come back, right? And whenever he buys any other flavor, he will take some time to come back. So ultimately, the issue was not the ice cream, the issue was the time to restart the car after shutting it down. So whenever the car is turned off, and he comes in certain time. If the time is less, the car was not starting, and if the time is more, the car was starting all right. So that engineer identified this issue, that it is not the ice cream, it is the time taken, right? And finally, he identified that it is a problem of something called vapor lock. In combustion engine, whenever there is a piston, the basically due to combustion, your fuel is getting vaporized. Okay, and when that vaporized thing is basically getting into your fuel injection system, then it will basically block the fuel from coming into the combustion area. Okay, so that was what was happening. So the moment you say that the car was taking less time, the person was taking less time to come back, he identified that okay, this is because of that vapor lock, the car was not starting. After some time, the car will get cooled down, and automatically that vapor is again uh, setting down, and you can start the car again. So ultimately, it was the vapor lock which was happening, and the engineer suggested that you should basically add some extra washer or something to the piston mechanism so that that vapor lock does not happen. So ultimately, it was a physics problem, engineering problem, you can say. Right? This is something which has really happened. If you search on internet, you will find the whole detail. Okay, this is one link which I have given here. I'll share this presentation if you want. Okay. Yeah, I think is it time to close, or do we need to continue?
Depend on yourself. If any point is not remaining, then we can close. Otherwise, if any point
No. This is just out of this is extra discussion. This has nothing to do with what we are discussing right now. The question is that you can show this thing to your students, that sometimes it happens that something is apparently not looking as a physics problem, right? But if you check carefully, there might be something which is physics in there.
Yes, sir. Sure.
Right? Yeah. Just to share an example, nothing else. There are many more on teaching methodology and how to think, in what way one should interact with the students. There are many stuff like that, but that we'll discuss at some other point of time, not now.
Okay.
Yeah. So if you have any question, you can ask now, or we can close if it is over. Yeah, could you get something from this?
Sir, it was a great discussion. Thank you so much for this wonderful session.
Okay, thank you.
Yeah, it was great. Good. Thank you, sir.
Yeah, thank you all. Yes, Manan, can we close now?
Okay, sir. Thank you.